Okay, hi everyone. Assalamu alaikum.
Waalaikumsalam.
This is Cihat Abdioğlu from Kahramanmaraş Mehmet Bey University, as he said, from Turkey. First of all, I would like to thank to Professor Inda, who invites me here to give speech and to make some research. I am very happy to see you all here, and I am very happy to be here. Today, I will try to talk about a little bit graph theory. And inshallah, I will start with some basic notions, and then I will show one of our papers, one of which is with Professor Shakir Ali. Then, inshallah, I will try to lead you, I will try to open you a new area and a new, some new topics. So, is there anyone who study on graph theory here? Some students or?
No, please,
You? Please don't be afraid. I will not ask you any hard questions. You? Sorry.
I work on graph theory and particularly correctly, and also just start with algebraic graph.
Okay.
At the beginner.
My PhD or my master is not on graph theory, but after some time, we lift module theory, and especially module theory. We defined lifting modules, then FI lifting, then PI lifting, stronger lifting and extending. then when we couldn't lift or extend much more, then especially after my PhD, I was alone. Then I started to research, started to looking for a new area. Then I started to study on graph theory, and alhamdulillah, I have some good papers with other researchers, with Professor Shakir. So, do you know where the graph theory emerged? Especially, I asked for the young researchers. No. Oh, okay. Let me show. Its origins goes back to 70s. It emerged from Euler's problem. It was called Königsweg bridge problem. I will show the picture now here. If the 7 bridges of the city of Königsweg, there are some rivers, and there are 7 bridges, then can all be traversed in a single trip without doubling back. You should use all bridges only one time, and you should have used one time each bridge, with the additional requirement that the trip ends in the same place it began. He asked if it's possible or not. So what do you think? You can easily try it. Start from one point, then across all bridges, and then can you come back the same place? He replied that problem negative. It's not possible to make such a trip. Then it's accepted the study of topology also. Yeah, because in topology we have very different surfaces, very different spaces, and at that time also accepted as the starting point of the topology. As I said, Euler proved that the problem has no solution. Euler first pointed out that the choice of root inside each land mass is irrelevant, and that the only important feature of a root is the sequence of bridge close. This allowed him to reformulate the problem in abstract terms. Now, he started from the real problem, then he brings the problem to the algebraic structure. We can find it's in a Foundation of Graph Theory book. Eliminating all features except the list of land masses and the bridges connecting them. Now we started from that area, Then we picture the second one. Then he wrote it in the last right one, modern terms. You see here, we call the masses, the lengths, as vertex. In graph theory, we call them vertex, and the lines called edge. So now we can study on that shape. It's in we can see the problem in graph theory, but we usually study on single edges. Not here we have, for instance, two edges in between two vertices, but we usually study on the one with one edges. Actually, we use that graph theory, that graphs. I am sure all of us use it in our daily lives. Can you guess what's it? In our mobiles.
Network.
Which one? Networks, yes, but more common. Google Maps, of course, yes, because when you write some route in Google Maps. Sorry? Yes.
Most important now is electricity.
Yeah.
We crowd, we have car, so you use GPS when you want to go and go without any.
It gives you all roads and it calculates the shortest one.
Most important is
Yeah. So the cities or the streets are the cities are the vertices and the roads are the edges. Yeah. And one more, please. I think in Asia countries, Facebook is very common.
Yeah.
Right? We use Instagram instead of Facebook. But so an undergraduate of the Facebook, it's only graph theory. Why?
Mutual friends.
Yeah, because the peoples are the vertices, and the edges are the how to say. For instance, I know now Musa. We have one edge between Musa, and we have edge between Inda and Shakir Ali, and now I have I extend my graph to all you. Yeah. And it uses also to give some permissions to you. For instance, I know Musa, and Musa knows her. What's your name? Era. Musa knows Era, and Facebook wants me. Maybe you should. Yeah, you're red. Yeah. Okay. Oh. That's the problem.
If it's complex here.
What is the meaning of
Pacil,
this?
pacil.
335. It has an understand yourself?
Panggil Pak Cil.
Musa?
Yes, sir.
6335.
This is from the computer. We are asking the technician first.
That with the graph.
There is cryptography.
Yeah. Okay. So please.
Graph, yeah. Ask me the technician.
Okay.
Yes.
Okay.
Because the slide here, you can see the slide here. Nggak bisa. 6335 juga nggak?
No, it's goes in.
Okay.
So I should use it in every moment, right?
Okay. No.
Okay. Okay. So here. No, okay. You know what?
Okay.
Okay. So what we need when we try to draw a graph, mainly we need two sets. VG, the set of the vertex set of the graph, The second one must be EG, the edge set of the graph, and we need one relation between the vertices. If two vertices in a graph are connected by an edge, we say the vertices are adjacent. So we are adjacent with Musa, with Inda, with Professor Shakir Ali. And G denotes the chromatic number of the graph. Chromatic number, we started with Beck. Inshallah, I will show you later. The minimum number of colors which can be assigned to the elements of R in such a way that every two adjacent elements have different colors. So suppose I colored with white, Musa cannot be colored with white. So we should change, we should choose another color for him, also for Professor Inda. And the graph is called connected if there is a path between any two distant vertices, and called complete if all vertices are adjacent. So if we suppose all of us as graph, what do you think? Is it complete or not? Not complete, because we don't know each other, right? And connected is our graph is connected.
Yeah.
Because
connected.
Yeah, connected means when you start from one point, then you can go by following the roads, the edges, then you can go any other vertex. So for instance, when I want to meet some of them, then I go Musa and Musa's relation, others, then we can, okay. I will come to algebraic, but since many of you don't know the graph theory structure, I follow that way. Okay, and in graph theory there are many definitions. I gave some important ones here. One is the clique number is the greatest integer such that Kn subset of G. Kn means the complete graph with n vertices. And the distance between two distant vertices A and B, denoted by DAB, is the length of the shortest path connecting A and B. Of course, we don't need to have such path. If such path does not exist, then we write it as infinity. It's clear that the distance of the same vertex to same vertex is 0. Yeah. And shortly, we can define maybe it's understood more easily. We can define the diameter as the supremum of DAB. We calculate all distances between vertices, then we take supremum. And one more important definition is the Girt is defined as the length of the shortest cycle. Cycle means, you know, a closed work, like triangle. Okay. So, the zero divisor graph were first defined for commutative rings by Beck, but he let all elements of ring as vertices, all elements, including 0. Okay, but he was mainly interested in coloring. Why we are studying in graph theory in algebra? What is the advantage of it? Because when we draw the graph, then when we look the graph, we can understand the structure of the ring. As he asked the same question, why since we have the definition of commutative ring, why we are studying the derivations? Because when we study with derivations, then we can understand under which condition the graph, the ring is commutative. So when we look the graphs, then we can understand we can explain some important explains of the rings. Okay. We consider R as a simple graph whose vertices are the here, many times we use commutative rings. Why? Because the graphs, we can divide the graphs in two ways. One is undirected, one is directed. For instance, up to today, suppose the professor knows me, but I don't know her. So edge from her to me exists, but now edge from me to her also exists. This is called a directed graph. But we usually, to eliminate that, we use commutative ring. Because suppose here, the vertices are elements, two different elements, x and y are adjacent. If and only if xy is 0, that means yx is 0, it doesn't matter, xy or yx. That's why we use usually commutative rings. Okay. Here's some results of Beck. Chromatic number is 0. If and only if R is the 0 rings, and chromatic number of the graph is 2, if and only if R is an integral domain and or R is amongst them, you can start that paper, Beck's paper and Anderson-Livingston's paper, to understand the structure of the graph theory. They are not so difficult. Okay. Because you can draw, for instance, the graph for Z4. Okay, because there are 4 elements, 0, 1, 2, 3. Then you can draw it easily. Okay. So in Beck's, please note that he take also 0 as vertices, as vertex. 0 is a vertex in his study. So that means 0 is connected to others, right? So when you color 0, for instance, in red, then you should color others in another, because they are not adjacent, right? Okay. Okay. Some coloring examples. There are some famous graphs. This is K6. This is C, cycle 5, C5, C6. You can see the chromatic numbers. Okay. Okay, so more important for us is that paper, which is written by Anderson and Livingston in 1999. Anderson and Livingston introduced and studied the zero divisor graphs whose vertices are non-zero divisors of a commutative rings. Okay. They studied the interplay between the ring theoretic properties of commutative ring and the graph theoretic properties of its zero divisor graph. That's what I said just before. When they look the graph structure, they can make some comments in for the rings. Okay. In the definition is almost same. What is the difference? They use not all elements. They use only zero divisors. Okay. So here are the examples. When you take Z4 or that ring, we have the graph as that. In Z9, what are the vertices?
0 and 3.
We eliminate also, how to say, the edge from itself. You understand it? We eliminate it. We don't take them.
3 and 6.
3 and 6, yes.
Oh.
Yes. Because multiply 3 and 6 gives 18, which equals 0. Okay? Here, Z6, the graph of Z6, zero divisor graph of Z6.
2, 3.
2, 3,
4.
and 4. So in middle,
3, 3.
3, yes. That's the graph of Z6 or Z8. You can draw more, and you can understand the graph theory structure from that paper and the examples. And as you see here, they have some, they proved some results like here gamma R shows the zero divisor graph of the ring R. Okay, gamma R is the zero divisor graph of R. It's used many times. You can see it in many papers. Here, gamma R is finite if and only if either R is finite or integral domain. And zero divisor graph of the R, of the ring R. It's used in many papers. Here, again, if they find a relation between the properties of ring, which is R is finite and not a field, then the number of edges, it means number of edges of gamma R between 1 and infinite. Here gamma R is connected and diameter less than or equal 3. If gamma R contains a cycle, then girt of it smaller than 7. You can find the results in the paper. Again, graph theory properties. Under the condition, R is an Artinian, commutative Artinian. And they studied also under which condition the graph is complete. They studied under Noetherian case, finiteness case, or they investigate under which condition it gets a star graph. Star graph means in center we have one vertex, and I can show you here. Yeah, that one. That one is the star graph. Star graph with 6 vertices. Then I want to show you some more definitions, some more papers to show how.
Star graph has no connection with involution. Is there any connection? Yes.
I don't know but we should study on derivations with graph theory. Maybe we can.
There is a concept.
Why you think like that? What you see here?
No, I mean, you just say star.
No. Only since it
has no connection, has connection with it.
No. Probably since it's how to say,
but
similar with star.
But there is a concept on star and subgraph. Because I read some 2 people from India.
It's only for the similarity. And there are many papers, as you guess, on graph theory, especially on rings. One of them is ideal-based zero-divisor graph. I will come from ideal-based zero-divisor graph, one of our papers, which is quasi-primary ideal zero-divisor graph. Here, Redmond, in his PhD thesis, they studied that concept. They defined it. When you see the definitions after published, you will see that it's not so difficult to make some definitions. You will see, inshallah. I will show you how to make such definitions. Here, they studied on, again, commutative ring and IB and ideal of R, and they defined an undirected graph with vertices. The elements of X are not in I, XY in I for some, Y is not in R, not I, where distinct elements X and Y are adjacent if and only if XY in I. Here, they first, as I told you before, first they define the vertex set, then they define the adjacency rule. The adjacency rule here is that multiply of X and I must be in I. Then we call X and I are adjacent. Then they draw the graphs like that. But here you can see xy in I. When you multiply, then you can see the result lies in I. Okay? And they, again, since it's ideal by zero divisor graph, you should, it's better when if you search the connection between zero divisor graph. It's very common. For instance, it's very clear that if I is zero, then the gamma zero divisor graph, right one is zero divisor graph again, becomes the same. Zero divisor graphs and the ideal based zero divisor graph became the same one. Okay? And let I be a non-zero ideal of R, then ideal based zero divisor graph is empty if and only if I is a prime ideal of R, and it's not so difficult. You can find all proofs in his thesis, and they again have some explore the relationship between gamma IR and the quotient ring. Okay. Then we studied quasi-primary ideals and ideal-based zero divisor graphs, motivated us to define a new graph containing elements of that ring as vertices. We defined ideal-based zero divisor graph and published in Hacettepe Journal of Mathematics and Statistics, which is indexed in SCI Expanded. The ideal-based zero divisor graph, we show it Q gamma IR, like Redmond's definition. And it's undirected graph with vertex set, and two distant vertices are adjacent to the same. But here, what we did, we changed the vertex set, not adjacency rule. The adjacency rule is similar, the same, and we got some. So since we defined that concept, since it's a new concept, first we want to see the graphs, and again the interrelation between ideal-based zero divisor graph and the zero divisor graph. So that's why we gave some basic examples in the paper. I took here that examples and results from the paper. We in the first example we take R as Z6 and the ideal is 0. Then all graphs, ideal-based quasi-zero divisor graphs, ideal-based graph, and the zero divisor graph are coincide. But we should find another examples, of course, under which conditions they are different. And we can see in the next one, these two are, we can see here. Yeah, we can understand better here. Here, yeah. For Z6, all are coincide, all are the same. But when we take Z12, all are different. Here, different means is not about the shape. The graph properties are different. They are not isomorphic. Okay, so you can draw that graph in many ways. For instance, you can take that one here. We have rectangle, right? So whenever we make the definition, we directly focus on the examples. Under which conditions are the graphs are same or not? Then after these two examples, we decided, alhamdulillah, they are not same, and then we go on the other properties, the theorems and propositions. Trivial relations and examples showing that under which condition these two graphs are coincide, and graph properties of ideal-based quasi-zero divisor graphs, such as diameter, gauge, chromatic number, etc. There are many graph theoretic definitions you can study on, and we study ideal-based zero divisor graphs of Nodarian multiplication rings. We calculated the clique numbers and the others. Here, some of our results you can see also in the paper, inshallah. Here we calculated diameter and girth in some cases. Oh, this is another one, another definition from us, which called Armendariz graph. It's not so hard paper. In discrete mathematics, algebra, and geometry, which is non-SCI journal, but sometimes we need such type of papers also. I can prefer you to make such definitions. The definition is too easy. We take vertices as the polynomials. See here, Aitchison's rule. Whenever we product the polynomials, you know, we don't need to get AIBG is 0. So we called here if multiplying FG0 gives AIBG is 0, then they are F and G are adjacent. Okay. Then again we got some examples. Here we have we already have gamma Rx, zero divisor graph of Rx already done. So we again made the same. We investigate the similarities and the differences between already known graphs. Okay. Then we show that again, alhamdulillah, they are not same. Then we continue to check the other results. Graph theoretic, as you see here, graph theoretic results. Where under which condition the graph is bipartite, what's the diameter on under some conditions, what is the girth, what is the relation between the known graphs and our graphs. Like that. Okay, so some more graphs. I will come from that graph to our clean graph and clear graph, inshallah. Again, not so difficult to define. Of course, the definition is not so, sometimes, usually not so hard, but exploring the properties, sometimes little bit hard, as you guess. Here the edges, vertices are idempotent elements. You can see idempotents of R are vertices. Two distinct vertices, X and I, are adjacent if and only if product of them both ways is 0. That's the definition. And many papers after this paper made by researchers, similar. So then, with Habibi and Yetkin Çelikel, Habibi is from Iran. Mohammed Habibi, maybe when you search on graph theory, probably you will see his name. We defined a clean graph. So our starting point is clean elements, as you see here. But when we finish the paper, we get some difficulty about some elements. Then we decided to take the elements like pairwise. EU, where E is an element, idempotent, U is a unit. Two vertices are adjacent if and only if EF is 0 and UV is 0. Then here we focused on the CL2. CL2 means we divide the vertex set to CL1 and CL2. If in case E is 0, then EU are adjacent to all. So it's not so. Then we get. So it's not so good. It does not give us good results. Then we focused on the CL2, in which we have E is non-zero. Okay. Here we can see the graph of Z6. You can see you can multiply, and we can here they are adjacent since product 1 is 1. Here 4, 3 gives 0. Here, another graph for Z12. Then, when I say the clear elements and clear rings, I thought that why similar to clean graphs, can we define the clear graphs or not? Then I defined, alhamdulillah, and share my definition with some of my colleagues. And here Akafa is my master student. Inshallah, will defend his thesis whenever I go back to Turkey. Then we define the clear graph. You know, clear elements is related with unit regular and unit element. An element is clear if it equals sum of one unit regular and one unit. An element is clean, it's idempotent, and unit here. So that again we established the graph. Adjacency rule, as you say, almost same. XY is 0, UV is 0. It's published in Indian Journal of Pure and Applied Maths.
Very good.
Just published, alhamdulillah. So we investigated the similar results. Again, we gave some examples to see the similarities and differences. We show the graph CR, okay, clear CR. We tried to draw it for Z2, Z3, Z4, Z5, Z6. Then we classify them. When we draw Z3, we get that one. And when we consider Z4 to Z5, we consider that one. Please look. K2 plus K2, K4, K44. K44 is a different type of bipartite graph. This is that one. Then we investigate the others, and then we have a general case, but I forgot to add it here. Okay, and we have, you can see inshallah the paper to see the other results. We have some more results, of course, in the paper. Okay, now I came to our one of the most important papers. It is new. Why I show? Please look here, all researchers, inshallah, because it's published in Journal of Algebra and Applications and newly defined. Alhamdulillah. I will show you, inshallah, many here. I will show you at the end, inshallah. Since it's new, there are many open questions on that graph. I will show you some of them, inshallah. Okay? Here, our vertex sets are non-zero proper ideals. Not so difficult. Distant vertices I and G are adjacent if and only if the summation of them is a prime ideal of R. That is the adjacency rule. Okay? In this paper, we study connections between, again, graph theoretic properties and algebraic properties of rings. The click number, again, when you define this a graph, first you should check the how to say, easier ones, like click number, Geert, and the chromatic number. There are many definitions. I cannot give all here. Domination number, independence number, like that. You can check all. Then we observed under which condition prime ideal sum graph is complete, and diameter and Geert of prime ideal sum graph are studied. Here you can see some results. Here, prime ideal sum graph is R, has a universal vertex if and only if these two. So when you check for a ring that prime ideal sum graph has universal vertex, then you can be sure that the graph, these two statements hold. Okay. Okay. Here again we have another result. When you can see the graph theory property here, radical of I is if radical of I 0 is a universal vertex of pyramidal sum graph, then you have the other graph theory, ring theoretical properties. This is the advantage of the graphs. Okay. Again, isolated vertex. If I is isolated vertex, alpha non-diff, I is a maximal as well as minimal ideal of R, under which condition piece R is complete. So when you suppose you take a ring and draw its pyramidal sum graph, then suppose you get a complete graph, then you can be sure that R is a local ring and every proper non-prime ideal is a minimal ideal. Okay. Here again, we calculated the diameter, and here we calculated the girth. Okay, yes. I took this from the last night from the Google Scholar citations to show you how they study on our new defined graphs. Here, for instance, embedding of prime ideal sum graph for commutative ring on surfaces. Metric dimension in a prime ideal graph. And strong metric dimension, they studied strong metric dimension. And they characterize prime ideal sum graph under which condition planar, toroidal, projective planar. These are graph theoretic properties. Okay. Here, on rings whose prime ideal sum graphs are line graphs. As I see, P methyl, focus on our paper. Here, methyl. You found good open. Okay. So I can suggest you to focus on the prime ideal sum graph. Also, we have some papers on prime ideal sum graph. After the graph indices, I will show you, inshallah. Here, there are many. There are many graph indices. I want to talk a little bit about the graph indices. There are many topological indices. They are distance degree or distance based or degree based. Here, the first one you can see Wiener index of the graph. I recommend first you can start from the calculating these indices. For instance, here, look, Wiener index. You calculate all distances and collect sum of all distances. Then you got Wiener index. Here, forgotten topological index. You can calculate like that. What you need to draw the graphs. When you draw the graphs, then you can see the edges and the vertices. Then you can calculate the distances, okay, or degrees. Then you can you can have some good results, inshallah. And in that paper, which is published in Current Organic Synthesis, we calculated forgotten topological and Wiener indices of prime ideal sum graph. Look. Of course, we calculated it under some conditions, like here. N is P alpha, PQ, P square Q, P square Q square, PQR. Maybe, but we cannot, how to say, we couldn't generalize it. So we cut it here, PQRS. Okay. Why we focus on these numbers? Because we start, of course, with Z2, Z3, Z5, Z6, Z12, Z15, 20. Then we got similar results. Then we classify them as you see here. Okay, so we classify Z2, Z4, Z8, ZP to the alpha. Okay, PQ we calculate Z6. So Z6 equal 2 times 3. You can see it in PQ. Let me show you the graph here. Okay, here Z P to the alpha. The graph is like you can take here. You can choose specific P and alpha, and you can calculate. You can see the other graphs. Okay. Then now we know the distances here. Okay. Or degrees. 1 degree base. 1 1 1, and here alpha minus 2. Okay. Then we get these indices. Again, here you can see 7 to the 8. If you take n as 7 to the 8, then you can calculate as you see here. Okay. Its forgotten topological index becomes 222. So there are maybe more than 1,000, maybe more than 2,000 indices, graph indices. Here we calculated only 2, forgotten topological index and Wiener indices. So maybe it gives you a starting point to make some, how to say, non-SCI journals or some presentations in some conferences. You can calculate some other indices and then get good results. Okay. And the paper, after this paper, alhamdulillah, we get the better one with Professor Shakir Ali, computing topological disciplines of prime and distant graphs of commutative rings and published in Symmetry. You know it's a Q1 journal. Here we focused on, again, the same numbers, but we focused on the polynomials and polynomials. Okay. Now I will show you, inshallah. Here, the polynomials are very related with the indices. You can see here topological indices. So as I told you before, we calculated it for forgotten topological index and Wiener index. For instance, second modified Zagreb index also you can see here. You can take prime ideal sum graph and you can calculate some others. So not so difficult, as you can see here. Okay. Only you will see the degrees and follow the formulas. Okay. Harmonic index, inverse sum index, Zagreb index, second Zagreb index, first Zagreb index. There are many indices, and they are related with the chemistry. In that paper, we have a little application on chemistry. In the drug industry also, graph theories are very related. Here we have the polynomial. You can see the similarity between the indices. Okay. Again, in other condition, P square Q, if we take the ring as ZP square Q, then we get a polynomial like that. Okay. Okay, that's all my talk. Thank you very much. If you have any questions, inshallah, we can discuss. We have time later, probably, inshallah, we can discuss. Maybe they can think today, we can discuss tomorrow. We have time and we will meet again, right? Okay, inshallah. I want to show you, if there is no questions, a little bit about TÜBİTAK and Turkey, my state.
Thank you very much for this wonderful explanation about the graph notations. So, like you calculate graph indices, similar kind of graph indices. Okay, several people have following it. So, what is the role of graph indices in graph theory, and in other area? I mean, why we focusing on that?
They are related with the drug industry, but I'm not so expert in that part. We can when we calculate it, we can make some comments on atomic structures.
Atomic structure.
Yeah, atomic molecules and the graph. They are sometimes they are very similar, too similar.
If you have a number of multi-index, more index stuff, but we have two molecules. One has like 400, another has 500. So which of them is more good or more? In fact, they are more.
It's a very wide area.
I think about the role of the indexes. Why they are focusing on that. Yeah. Anyway, this is my comment because this paper I already have, and I have one open position followed by then one. Okay, go on with last result. Yeah. So the open question is I suggested and asked also the team who is present on this area, and it's still not find, but think you see the definition of n polynomial and com polynomials. Okay. So those who work in algebra, pure algebra, they can talk about these polynomials like, we found a ring with the help of polynomials. Okay? That is called polynomial ring. We call polynomial ring. So what if you think if you replace these polynomials by this type of polynomial, m polynomials and com m polynomials, so is this again form a ring, then what kind of ring is that? This is question open?
Yes.
Question. Okay, in that field.
Yes. If you success to define it, then it will open a new area. Yeah. As I remember, one asked the similar question to Esra in her speech in AME seminars. Still open, yeah. Yeah.
Algebra we are thinking if we replace these polynomials with a new type of polynomial, space polynomial. So it may be interesting to see its behavior when you correct, as I said.
And the others too.
Points.
I want to talk a little bit more about. Open. Yeah, this is Turkey map. I will show you, inshallah, where I came from. I will invite you to that so that you can decide easily. Oh, another one? Wait.
Maybe
JPEG? Maybe open with this one, JPEG?
Oh, so share.
Yes.
Share.
Yeah,
Okay.
this is one of the Turkey's map. I found it last night. So I checked tourist map, Turkey, some important locations. Yeah, you can see.
Which one is Karaman?
Where?
Which one is Karaman?
Where? Yes.
Which one is Karaman?
Which one? Do you know any? Please find Istanbul.
Istanbul is here.
Yes, Istanbul is here. A part of Istanbul is located in Asia and located the second part, Europe. Yes.
Okay.
And here is the capital city. Here,
Ankara.
Yes. Here is Konya. You can see.
Konya.
Very nice.
Karaman.
And where is Karaman?
That's near Konya.
Yeah,
Oh, here. Oh.
Yeah. And Maulana said that visit world, see Konya. That means when you visit Konya, then you can see the world. Yeah.
Oh.
And Mevlana's mother, how to say, Tom?
Yeah.
In Karaman. In Karaman.
So inshallah next year we have IIMP conference Azhar forum in Karaman.
Karaman, inshallah.
All are invited.
Inshallah, all are invited there. And we have airport in Konya. Also, please show Antalya. Here is Antalya, near the Mediterranean. Okay, Antalya. Yeah. If it's near, but it takes 3 or 4 hours to go by car.
Yeah.
Because there are big mountains. Mhm. Sometimes students before university opens the map, but they have weak geography knowledge. Opens the map. They thought that they are very near, very close. Whenever they come to Karaman, they say it's 4 hours. So I mean, you can come to Antalya by plane, Istanbul. You can find easily Istanbul flights in Istanbul easily. Then from Istanbul we have fast train. We went with Professor Shakir 1 time or two times. We use it maybe. Fast train, direct train from Istanbul. It takes over 5 hours. It's 800 kilometers. 800 kilometers, and we can go 5.5.
Very comfortable. That
Yeah. Everybody is sitting. Everybody has ticket, and everybody is sitting. No problem.
Istanbul to Karaman.
It's from Istanbul to Karaman. From Istanbul to Konya, we have also flights.
Then I think from Istanbul to Ankara. Ankara is also well-known city.
Yeah. Of course.
From Ankara.
Of course. Ankara is the capital city. Yeah. And I am from Trabzon. Please see. You know, everybody's Trabzon for us. The flag. Do you remember in morning?
Yes.
Yeah.
The east? Trabzon.
Yeah. Yeah.
Trabzon.
Very green. And near the sea. You can see the fish in my sea. Yeah.
Near the Black Sea.
Yeah, near the Black Sea.
Yeah.
Inshallah, on August, I will go. Okay, so everybody, I invite everybody, inshallah. You are welcome to come to my city. And please open the next one. I want to talk 2 minutes about it.
Okay.
About TÜBİTAK.
This one?
Yeah. It is TÜBİTAK, the Turkey Technological Research, Scientific and Technological Research Council of Turkey. Unfortunately, we don't have any postgraduate, postdoc fundings, but after PhD and therefore doctor degree, we have some research fellow program. So you can check the website to find some. You can write TÜBİTAK.
Oh, in the
TÜBİTAK.
website.
And then you can find out.
You can find out
kind of support.
supports. Yeah.
Research and for researchers.
Alhamdulillah, Professor Shakir came 2 times, inshallah, that year. Third time, inshallah, accepted our project, and he visited under the support of TÜBİTAK. Inshallah, your professors are welcome.
TÜBİTAK.
Yeah.
Oh, here.
Yeah.
First or second?
The same.
Okay. Same.
Okay. You can check the
Okay.
here.
But note down, we'll check. When you were asking the young guys, note down, then we'll check according to your requirement.
You can select the language and then see, inshallah.
Oh, there is.
Okay, thanks. One more. So listen me. Okay. Okay, please.
There's a question.
Thank you very much for that. So I'm interested about how you want topology in topological index of graph. Graph topology is concepts by sub collection of sub.
Yeah, but we didn't work on topological spaces. They called it topological index, but we only study on the formulate. So I don't know the topological spaces. Okay, maybe since you are studying on maybe that topic, yeah. You understand me? We only focus on the definition of topological index. We didn't think why we call it topological index. We only use the formula. Okay. Maybe one can check why it topological index, then maybe you can define some more index. So there are almost 3,000 indices.
Because I know graph topology is processed by collection of subgraph. So I think it's related with
I don't know. Maybe. Graph topology is another area.
another.
Yeah. Okay. Thank you. Okay. Thank you very much.
Okay. Thank you very much, Professor. Any other questions from the participant or maybe in the Zoom? There is no question in the Zoom, so maybe from the participant here, there any other? Yes, sure. Perfect.
About the annotation you use in your paper clean graphs, you use like a plus. Is it that one is the union or something else?
Yeah. Union.
Oh,
Union of. So we have two graphs, K2. When you draw the graph, you can see it is easily.
Okay. Thank you, Dr. Yani. Also, maybe any other questions from the participant? No? Oh, maybe there is one question from me, Professor. You mentioned about toroidal planar graph. Is it what you said related to topology or?
Yes, it's related.
So
planar means you can see it in a two dimension space. Yeah, toroidal you cannot see draw it in 2 dimensions.
Oh,
yeah.
so
Planar means planar. You can draw it without crossing edges on the plane. It means. Yeah.
And also for clean and clear graph, yeah. I noticed that the definition of clean ring is quite familiar here. But for the clear graph, is there any such thing as clear ring? Or?
Yes, sure.
Yes.
Yeah, it's my. Please open the
clean
maybe
graph.
No, open the internet.
Oh, the internet. Yeah.
Please write clear graph.
Clear graph. Okay.
I didn't understand why people not studied much more on clear graphs, because the paper is published in not Appiolo, only clear graph.
Oh, only clear graph.
Clear ring. Yeah.
Clear graph.
Well, as I remember, published in non-SCI journal that
clear rings.
Yeah, that one.
Yes.
No, please go back and open it from the journal.
Oh, open for the journal. Okay.
The second one, well, I think that. Yeah.
Oh, here.
Zabas, yeah.
Okay.
As I know, it's not non-SCI journal.
Okay, here.
Yeah, PDF, right?
Oh, PDF. Okay. Clearings and clear elements.
When I see that paper, I decided to define the clear graph.
Oh, okay. But the definition is different to clean rings.
But very similar.
Similar,
yeah. Please see. Clear if it's sum of a unit, regular and unit.
Oh, so in clean ring you have regular,
idempotent and unit.
Idempotent and
clean. Here, unit, regular and unit.
Oh, okay.
Yes.
So there is similarities between clean rings and clear rings, as well as clean graph and clear.
Yes. First, I check for some specific rings,
yeah,
whether they are same or not. When I got results different, then I said, Alhamdulillah, we can go on
clear graph.
Yeah, clear graph.
Oh,
yeah. Otherwise, they are similar. They are same.
Okay.
Of course, they are similar. Under and also we determine under which conditions they are coincide, under which conditions they are different. Okay. Then when we make sure as they are different, then we go on to study to check the other properties.
Okay. Thank you very much, Professor Jihad.
You're welcome. If you need any papers, any books on graph theory, I can share you via Google Drive. Inshallah, I can collect you. Please feel free to ask me, to write me. I forgot to write my email here, but maybe Professor Indah has, or maybe I can send you, and you can. Or also you can see on the papers, no problem.
Oh, there is.
Please feel free to write me.
Inshallah. Okay. So for the information, Professor Jihad will also be here for 1 week. So for those who wants to ask directly to him, you can also just come to his room in which room? The 5th floor.
New building.
Okay, so you can come in the 5th floor in the new building of our department to ask directly to him. Let's all give applause for him once again. Thank you very much, Professor. So for now, we have break for 5 minutes. There are some snacks, and also for students, you please do the sign. Yes, the sign also scan the QR code to sign, and also we can distribute the snacks for our break 5 minutes. Thank you very much, Professor Jihad.
You're welcome. Welcome.